Zhanni Gao, Yirong Jing, and Lingyao Meng are presenting to you the effect of changing the parameters on raw data on the hockey stick controversy. Hockey stick controversy mainly revolves around two previous researchers on this topic. Michael Meng, Raymond Bradley, and Malcolm Hughes developed a statistical methodology that provides evidence that temperature is uniquely warm in recent years. On the other hand, Ross McKittrick and Stephen McIntyre argue that statistical errors in Meng's method has bias towards the presence of global warming. After which, we're going to give a step-by-step introduction of methodology used by both papers in the generation of data and the principal component analysis on the generated data. We will then introduce you our research and conclude this presentation with our critique.
Here are some research on global temperature before Meng. Graph on the left is the real temperature during last century. On the right, a graph by the Intergovernmental Panel on Climate Change from 1990 shows a historical natural fluctuation in temperature. Judging from this graph, it seems that the temperature rise after 1900 is a work of nature instead of mankind. Is this true? Meng, Bradley, and Hughes' research in 1998 provided some evidence to shed new light on the issue.
In 1998, Meng, Bradley, and Hughes published their research on Nature about annual global scale temperature. The graph of real temperature shown is generated by Meng, Bradley, and Hughes in the 1998 paper. From the graph, we can observe that the temperature rises sharply around 1900, while the reconstructed temperature before 1850 stayed fairly constant. This graph is called hockey stick. In their paper, Meng, Bradley, and Hughes used principal component analysis on the range of variables, such as tree rings width and ice core, to estimate historical temperature back to the 15th century. Based on their study, they argue that the increases in global warming is induced by humans, since the rise in temperatures corresponds to the Industrial Revolution. In their 2003 paper, McKittrick and McIntyre claim that there are issues with Meng's statistical methods, which has a bias towards the presence of hockey stick-shaped graph. McKittrick and McIntyre attempt to use Meng, Bradley, and Hughes' algorithm to reproduce the hockey stick graph. However, Meng refused to publish their data. McKittrick and McIntyre instead generated random data to provide evidence of the bias in Meng's method. Although they're not to deny the pattern of recent global warming, they suggest that Meng's paper does not provide evidence that the 20th century was uniquely warm. In Meng's paper, 4 main steps are involved in generating the estimated historical temperature. Raw data is standardized before principal component analysis is performed, and PC1 is used to estimate historical temperature. In a proper standardization, the difference between each variable in each year and the mean of each variable for all years is divided by the standard deviation of the variable for all years. However, in Meng, Bradley, and Hughes' research, they took the difference between each variable in each year and the mean of the last 79 years instead of 581 years. Thus, Meng's estimated historical temperature will deviate from the reconstructed temperature with correct standardization.
McKittrick and McIntyre could not access Meng's original data, and hence they have to generate 70 sets of red noise data for 581 years. Red noise data are data that has no systematic pattern except some correlation between adjacent years. Hence, we would not expect red noise data to be moving in any systematic pattern in the long run. The first step in the generation of red noise data is to randomly select a value for a particular variable x1 in the first year from a normal distribution. The mean for the normal distribution is set at mu, while the standard deviation is set at SD. For subsequent years, Value for the variable x is generated according to the equation shown, where value for x this year is a function of value of x in the previous year plus a random error term. More intuitively, each x represents temperature in a year according to one variable. We generated 70 sets of red noise data using the method described in the previous slide. Here are 6 sample plots of red noise data. The parameters used in the generation of this set of data are the following. The mean is 0, SD is 0.276, and beta is 0.415. These values are average values of parameters used by McKendrick and McIntyre in their paper obtained from Meng's original data. We can see from the plots that all sets of data do not follow any systematic pattern, which is what we would expect for red noise data. After obtaining different sets of red noise data using the method described previously, the red noise data is standardized using both proper standardization and Meng's standardization. We performed principal component analysis on both types of standardized data. PC1 using properly standardized data shown does not show the hockey stick shape. However, PC1 using data standardized by Meng's method has an obvious upward trend in the last 79 years, showing the hockey stick shape. We should keep in mind that these plots are generated from random red noise data with no systematic pattern. However, is it possible that this hockey stick shape is a coincidence? The answer is no. Here are 10 plots of 10 simulations of PC1 using Meng's improperly standardized data. We can see that the hockey stick shapes seems to be present in all 10 iterations, suggesting that Meng's method seems to have tendency to generate a hockey stick shape even for random data. Now, for our research, we want to investigate the effect of changing parameters used in the generation of the red noise data on the presence of the hockey stick shape. The equation used by McKendrick and McIntyre is shown. Intuitively, we can see that beta measures the dependence of current year value on previous year value. For example, if the variable is tree-ring width, a positive beta would suggest that a wider tree-ring last year would increase tree-ring width this year, after accounting for the random error term. Mean represents the population mean of each variable, while SD is the population standard deviation of each variable. After knowing the intuition behind these parameters, the question we want to investigate is, what is the impact of altering these parameters on the appearance of the hockey stick shape? Here are 10 different values of mu, standard deviation, and beta. In our study, we ran 10,000 iterations of PC1 for each combination of the parameters. For the determination of the hockey stick shape, we referred to the standard error. The standard error is equals to the difference in mean between the last 79 years and that of all 581 years, divided by the standard deviation of 581 years. We cite the criteria at one standard error, and when SE is greater than 1, we conclude that the hockey stick shape is present. In order to investigate the relationship between the raw data parameters and the proportion of hockey stick shapes, we vary values of mu, SD, and beta while holding other parameters constant. Recall, we determine red noise of first year by randomly select a value from a normal distribution, which has mean as mu and standard deviation as SD. Beta determines how much raw data in this year depends on data in last year. In the first graph, we vary mu by -1, 0, and 1. The graph shows that the proportion of hockey stick shapes under Meng's method is much higher than that of proper standardization and improper standardization of the last 40 years. However, the proportion of hockey stick shapes does not vary as mu increases. Similarly, in the second graph, that the value of SD does not greatly influence the proportion of hockey sticks. Nonetheless, Meng's method generates a much higher proportion of hockey stick shapes. On the other hand, the third bar chart shows that the value of beta strongly affects the proportion of hockey stick shape for each method. As beta increases, there's a growing proportion of hockey stick shape graphs. Therefore, we conclude that while values of mu and SD have little effect on the proportion of hockey stick shapes, values of beta are very influential on the likelihood that the hockey stick shape occur.
To investigate how value of beta influence the first principal component, we first look at how the value of beta influences the raw data. We set mean and SD to be 0 and 0.276. We simulated 4 groups of raw data with increasing betas. Each group has 70 random red noise for 581 years. From left to right, we are showing 4 of 70 random red noise for each value of beta. In the leftmost graph, from up to down, are x1, x2, x3, and x4. All of the 4 red noise data have the similar distribution in time order. However, if we compare the 4 sets of raw data in the slide from left to right, we conclude that as beta increases, the red noise becomes less random in time order. This observation is reasonable because as beta increases, the dependence of the current data on previous data increases.
Next, we present how values beta affect the proportions of hockey stick shapes. Following Meng's method, we perform principal component analysis on sets of raw data. We assign 4 different values beta while holding mu and SD as constant. We repeated this 4 times, and the graphs show 4 same results for each beta. We can see that as beta increases, the more obvious the hockey stick shape is. According to what we have observed, we conjecture that in Meng's method, a greater beta will generate upward bias on hockey stick shape in principal component analysis.
In this table, we summarize the proportions of hockey stick shapes among 10,000 iterations with 4 different values of beta. For each method, vertical comparison shows that as beta increases, the more frequent the hockey stick shapes occur. Also, we can compare 3 methods across the tables with the same beta. For example, 0.415, Meng's improper standardization generated the greatest upward bias on the hockey stick shapes. However, this bias was reduced through improper standardization of last 40 years. More significantly, the bias was reduced almost to 0 on the proper standardization. We conclude our presentation. According to our study, first, Meng's method generates significant bias toward the hockey stick shape. Second, mu and SD of time series do not contribute to the hockey stick shape. Third, greater beta of time series does contribute to the hockey stick shape. Last but not least, we want to emphasize that even though Meng's method was biased toward a growing trend in recent temperature, our research does not reject the existence of the global warming.
Our research provides implications on principal component analysis. First, principal component analysis is robust against the mean and standard deviation of proxy data. Second, principal component analysis is sensitive to correlation of contemporary data on previous period data. Third, however, our results are only limited to situations when beta is less than 1, so future research can extend to situations when beta is greater than 1. Here are the references, and thank you for your attention.